in all. Okay, let's see who'll be last. Guessing probably okay, still says there's only 5 people on. All right, so we're missing Hannah, Billy, Attila. Speaking of Attila, has anyone seen him recently? Yeah, because I think he wasn't on the last live stream as well, so might need to check up on him more than Hannah. That is wow. Could be to be fair. Yeah, to all right. We'll just start regardless anyway. They can watch it later on. Hmm. Fair enough. But then I guess in year 13 he would have probably missed a lot of the content. Oh well. All right, let's just start. So we done this last time. We talked about diffraction gratings, um, and we just mentioned how like they allow light to be diffracted and you get these fringes there. Today we're basically moving on to this. So this is the title for today. If you guys want to take it down. So Young's double slit is very similar to the diffraction gratings practical that we done in class. It just has a bit more math, I think. Okay, so the setup or the way this works is we're going to shine. Let's imagine this blue pen is a blue laser, right? So I'm gonna shine blue light, and when this blue light goes through these gaps there, because it's called Young's double slit, it only has two gaps, if that makes sense, yeah. Whereas the diffraction grating that we done a few weeks ago had like I don't know, like about 600 or 700 gaps per millimeter, so it's a massive. So this only has two, and the way it works is when the blue light goes through here, it diffracts, and then we get bits where we get constructive interference, aka where the light or the waves basically meet up and then they increase the amplitude. And then also we got points, the white points there are the bits where there's destructive interference, so where they cancel each other out. So the key thing is, they could ask you in the exam, what do these bright spots represent? You just have to mention that they represent points in which this occurs. Yes, if I were you, I'd probably just draw this. So you just have what's it, a gap there, or two gaps there rather. You have a laser light, aka monochromatic, and it's going to hit this screen, and you basically just get dots. Now, unlike diffraction grating practical, the previous one, where on the screen we said that all the dots, all the fringes were had the same brightness. In this case, with Young's double slit, the brightest or the middle dot's going to be the brightest one. And then as you go further onto the sides, they get dimmer and dimmer. So you start off with something incredibly bright, then they get dimmer until you barely can see it towards the end. So that's the key difference between both practicals. Okay, now you can kind of represent this on this graph. They do ask you this in year 12 and year 13. It's just an intensity graph. So let's imagine there is no y-axis per se, but if we did make a y-axis here, this would just be called intensity or how bright the dots are. This is basically the middle. And as we said, the middle dot or the middle fringe is the brightest, so it's just going to be the highest in terms of intensity. Then as we drift off to the sides, it's going to get less and less bright. You should be able to draw this in the exams. I mean, there's like every year or every other year, they always give you a question for 2 marks where they ask you draw how monochromatic light hitting the screen via a double slit would be represented on this intensity graph. A key point here is, despite the brightness changing, obviously we said the brightness there and it gets dimmer and dimmer, the size of the dots is the same. So maybe I should have made it a bit more accurate, but the size of all the dots are the same. AKA, that means the width of all of these profiles are the same as well. So each one roughly spans like a whole gap or whatever that length is, all of them have roughly the same length. Yeah, so that's the key thing. So if I have to draw it from scratch just for you guys to see it, they usually give you like loads of these lines like that. Just make sure in the middle you start off with something quite high, and then just keep going a bit, and then keep just going a bit lower. But try to make sure the width is roughly the same in each case. And it needs to be symmetrical as well. Whoops. So that's quite important. All right, that was terrible, but you get the gist of it. So that's one thing you need to do in the exam. Now, definitions, right? Because I don't think we've done this in class before. When we talk about the conditions for this experiment, or for you to get those fringes, these are the two conditions we need. This is probably the most important two sentences in this lesson, so you might want to write it down. So two conditions needed for, what can we say, Young's double slit experiment. So what we say is the incoming light, or the light, basically has to be coherent, which means that it has a constant, wait, what on earth did I write there? Phase difference. So I don't know why I said diffraction. Yeah, so it has a constant phase difference. All that basically means is that all the waves have the same, the same distance between them. And I'll go more in depth to explain what this is, but just for now, just take down the definitions. Monochromatic, we've done this in class before. It means it's the same color light, so you can't just say same color. We need to mention what the same color means. So same wavelength and same frequency, which you get if you use a laser. Yeah, so those are the two conditions you need, and you get this over and over and over again. Okay, now you see this experiment, what we can do is we can calculate the wavelength of light. So almost always, you're always going to be observing or trying to find out the laser light's wavelength is. There's a different formula for this experiment here. So we have this here. In your formula sheet, it does not give you, or it does not annotate these different symbols. So it's probably worth getting them down now. So I'll just explain these with reference to the picture on the other page. So W is basically the fringe spacing. By fringe, it just basically means dots on the screen. Yeah, so the actual dots on the screen, those are the fringes. So if I just quickly move here, these blue dots would be the fringes there. And this is the spacing. So it'll literally just be the gap between one and the other one, which you can measure using a ruler if it's the actual practical. This is wavelength, pretty sure everyone knows that. Capital D is the distance between this double slit there all the way to the screen. So there's that horizontal distance there. So that's that. And then S is the slit separation, so the gap there, basically. What is this? Yeah, so quite a straightforward formula. It'll just take a while for you guys to get used to what the symbols mean. But the key thing here is every single one of these are a measure of distance if you think about it, right? So they're all distance. So they're all going to be measured in meters. And they love in the exam giving you stuff in nanometers, millimeters, micrometers. So just always be sure to, change the units. Okay, now, this is like high level question. So this is, the W, yeah, sure thing. So W is basically the space in between two dots. So let's say you projected laser light through the gaps there. You get a profile on the screen. It's literally just going to be Oh, why is this thing not focusing? It's literally going to be this distance there between two dots, any two dots. And the thing is, the distance between any two dots is always the same. So they always have an equal spacing, if that makes sense. You're not going to have like one there, and then one all the way there. That's not going to happen. They're always going to be equally spaced out. So it's just a gap between two dots. Okay, now for an A star slash A grade scenario question, which they'll give you is they might mention explain. Yep, that is true, yeah. So like provided obviously you don't accidentally bump into the laser or like move the equipment around, it'll be the same, yeah. So the thing is, when we look at, for instance, this, let me give you a scenario which might prove problematic in the exam. Let's say this is your screen, and you basically have this as your profile, right? Do you guys think you can accurately measure this using a ruler? Or is there a slight issue? So it is about, I don't even know, just maybe about 10 or 8 different dots there. But as you guys can probably notice, it's going to be extremely hard to accurately find the gap between two, right? So it's going to be a massive issue, yeah. So what we need to do is, so what we can say is when fringe spacing is small, which it will almost always be, to ensure better quality results. It's so annoying being left-handed because when I write, you can't write at the same time. But when fringe spacing is small, to ensure better quality results, let's imagine that they told you there was 12 dots there, right? And then what we could do is we can basically measure the total distance. So let's say we measure the total distance and it gives us 12 millimeters for 12 dots, right? So let me just show you how this works. So we got 1, 5, 6, 7, 8, 9, 10, 11, 12. And they're telling you basically that all of this had a distance of 12 millimeters. To find out just one gap size, all you guys really need to do is just measure how many gaps there are. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So there's 11 gaps, right? The total thing is 12. So if you just want to find out the value of just one gap, what you could do is you can do 12 divided by 11. And then that gives you how much one gap is, if that makes sense. A common mistake that people makes is they see that there's 12 dots, then they're going to do 12 divided by 12, which is incorrect because you're looking at the gaps, the number of gaps, not the number of dots. Oh yeah, spot on, Leighton. Yeah, you could do that, yeah. Yeah, so that's just and with this is all about accuracy, by the way. It's not about reliability. Because I know there's always they love giving you questions where you have to talk about accuracy or reliability of results. Accuracy, remember, is basically getting results where you get a high degree or a better resolution, if that makes sense. The only way you can really do this is if you take a bigger reading to minimize the uncertainty. And if you minimize uncertainty, then you basically get better results. Now, so this is just how you just answer. They say, how can you improve the accuracy of your results? Literally, this is what you say. All right, so that's that. Now, you see with coherence, going back to this again, let me show you why you need to use a laser. So let's say we have the same setup. So we have a double slit there. You have your screen there. And then instead of a laser, let's say you have a filament lamp, right? So you have a lamp. Now the problem with this lamp is it's going to give light off in all different directions. And what we know is because it's giving lights off in all different directions, it's not, we can say basically the light is not coherent. And it's not coherent because it's not going through one specific focal point, if that makes sense. So light's not coherent, meaning that phase difference is not constant. Now, to put this in a more visual way, what a laser does is a laser basically allows light to only go through one point, right? So what I'll do is I'll just do another one now with a laser instead. So if I have my laser there exactly in the middle, shooting blue light, and obviously it'll have to be in the middle and at an equal distance from that gap and that gap there. So you can see mathematically, if the laser's the light source is at an equal distance from both, that means the light there and the light there will be in phase. Yeah, or they'll be in phase, which is a good thing. So that means that, let's say for instance, your screen is here, regardless of where the dots are, you'll always have like a constant phase difference. Now, it's kind of weird to explain this without showing you the practical in class, but for now, just understand that a laser light always allows the light to have a constant phase difference. That's it for now. And then when we go back to class, I can show you it in practice because otherwise it really doesn't make much sense. So the question will be, explain why a laser light is used. So you have to say it acts as a point source, which means that this will happen. Yeah, so light or waves will be in phase. Okay. Now let's try this question very quickly. So let me just write the formula for you guys. So W is equal to, try this question. I'll give you like a minute or so. Try to find out what the what's it called? Capital D is. So the distance between the slits and the screen. Yeah, so the key thing is just write down all the information you have. Let me just write on the bottom. Remember that W is the spacing between just two dots. So we have three dots, aka we have two gaps, so one gap there, one gap there. So what we can do is, if the total distance is 0.002, 1/2. Yeah, so I hope everyone got this information so far. All we're saying is basically the gap between two dots is going to be half of that number. So you just get 0.001. And then rearranging this to make D the subject, it will be so making D the subject, you will get W S over lambda, right? So you basically get that. And now if you put this in your calculator, let's see what we get. If anyone got the answer, you feel free to put in the chat 0.001. Oh yeah, spot on, yeah. So 96.77. Obviously, I just made up the numbers. That seems a bit unrealistic. Like we're basically trying to say that you have to have a distance of 96.77 meters away from the screen. But yeah. Oh, you can obviously tell that was made up. So that's how you solve these kind of questions. Obviously they could just be aware of the units in the exam. I made this a bit easier, but in the exam they could give you any type of unit. Okay, so what we've done so far is we just dealt with one color of light, and we just know that this is the formula that governs the relationship to find what the wavelength is. Now, another problem is that they can ask you, a theoretical one is, um, what they could basically say is explain how you could find or get values of W of better. So basically, let me just write the question. They'll say it's similar to what we've done before. So how to find W results. Now, as you guys can see by this formula in maths, you want this to be as large as possible because if this is large, that basically means indicates a large spacing, right? And if you have a large spacing, you can measure it better with a ruler and get better results. So if you want to make this quite large, you need to either decrease this. So you can either say decrease slit separation. You're just basically looking at the formula and just taking information from it. Or you can increase this, which is basically distance between the screen and the slits. They will not give you marks for saying increase the wavelength because the whole point is you just want to use whatever wavelength you plan to use to begin with. So either you increase this or you decrease that. Increase distance between screen and slits there. Yeah, so I mean, it's a decent topic. The question is always repetitive. Now here's for the A/A star bit. This is where you you have to use white light, aka all the colors, which is a bit weird, but yeah. Now the key thing is just so everyone. Oh, whoops. There you go. Oh, increase the distance between screen and the slit. So capital D value. Yeah, no worries. Okay, so that's everything you need to know for just using one specific wavelength or color of light. Okay, so if we look at this very quickly, does everyone still remember this from their GCSEs? Or at least from when we done this very briefly in optics, I think. So you just have to remember that yeah, red has the longest wavelength, and then violet. Obviously, violet has shorter than blue, but for whatever reason, they can't be bothered using all the colors, so they usually almost always use blue instead of violet. But yeah, that's just a rough indication. Um, so what we can say is let's look at this. What's gonna happen is you're gonna get white light, so you're not gonna use blue this time. So imagine this is a okay, nah, there's no such thing. There's no such thing as the laser that gives white light. So let's imagine, for instance, you just have a light bulb there, gives off white light. Now, the reason for the single slit there before the double slit, and this is very important. So we can say back in the day, so the guy's name was Young. I think it was Thomas Young. Yeah, they did not have lasers. So what they done was they used a single slit. So single slit is used to focus light. Yeah, so that's the only reason why you use this. The single slit basically it does not filter the light for you. All it does is it just allows the light to be focused from a specific point, like a laser point, and it makes it coherent, aka just have like the light will just have a constant phase difference. Like I said before, I'll show you this in class. Yeah, so that's why we use the single slit there. That's the only reason why we use it. So the light, so the if you had white light to begin with, it'll still be white. It'll just be it'll be focused. Okay, so the only thing they could do back then, ages ago, was because they had no lasers. If they wanted to get a specific color from white light, they would have to use filters. So I'm pretty sure I showed you these in class. Just like blue color, like paper that allows light to go through, and then it only allows blue light to go through, right? So they could have used filters. So what he could have done was place a filter there if you wanted, and then you'll just only get blue light. But let's look here and let's just assume that we're going to use white light. So you get white light going through here, it's coherent, it goes through both of the gaps, and this is what you actually see on the screen there. Now it looks a bit bizarre. What you need to understand is the middle or the middle dot or the middle like region or middle fringe is always only going to have the color white. So that's very important. So yes, you have to write down central dot or central what's it fringe is always white. That's why I just left it with no color. So that's your central one. And it's quite bright as well. Remember, it's always the brightest one. So we're still following the rules from the last page. So it's also the brightest fringe, the central one. Don't worry, you don't have to draw this. So central one is not only is it white, but it's also the brightest. And the key thing is, as you guys move along to the side, think about it this way. Red has the longest wavelength. So that means for your second fringe, so if you look, what I'm going to do is I'm going to zoom into this bit there. So for your second fringe, you kind of get something like this. So you start off with blue, and then you'll get something like green afterwards, and then you get red. Now, we know that red will always be furthest away from the center because it has the longest wavelength. If it has the longest wavelength, it basically spreads out the most. Yeah, so just think about it in that way. Longest wavelength, so it spreads out the most. So you get red all the way there. Whereas blue or violet is always going to be closest to the central fringe. Now, when they ask you in questions, they might mention, explain the position of the red and the blue, parts of the spectrum. You always have to mention their position relative to the middle. So what you'll say is, so you can say the blue parts of the spectrum. The reason why it's called the spectrum is just because it's like a profile for different colors together. That's all spectrum is. So the blue part of the spectrum is closest to the central fringe or to the center. You always have to make sure you outline it like this because a lot of students they understand it, but they just don't know how to word it or to say where is it closest to. So blue is always closest to there, and then we can say red. Wait, why the hell did I use green for the? Never mind. All right, the red part of is furthest from central fringe. Yeah, so I'll just leave this for you guys to copy. But the key thing is white light is a mixture of all the different colors because there's lots of different colors and different wavelengths. As it diffracts, due to the different wavelengths, you'll get red spreading out more than blue and green. Hence is always the furthest. Same thing applies as the previous page. Brightest in the middle there, then it gets dimmer and dimmer and dimmer as you go on the sides. Yeah, so from this part of the topic, I pretty much went over every single question in Exam Pro and how they would, I guess, word it to you. And this like all the solutions to them while explaining what the topic is. So they can maybe ask you what's the purpose of this? How would you see these profiles there? Where would red and green and blue appear on the spectrum? And talk about the intensity of brightness as well. Okay, so I don't know why I wrote that twice. I said reason for single slit, but I already put it on the other page. So that's fine. You don't need this. Okay, now the last thing for this topic is everyone done with this? Okay, yeah, so the last thing is I'll do it here just in case anyone's still copying. But you know that annoying intensity graph that we talked about? So one that looks like this, and then it just has lots of these lines like so. What they could do is they could ask you to draw, or they might give you the profile for maybe, let's say, blue light. So they might, let's start from the middle. So let's say something like this. And then it just keeps getting dimmer and dimmer and dimmer. Oh, I can never do this symmetrical, but oh well. So this is for blue light. What they might ask you now is draw this or draw the profile if you used a red laser. Yeah, so maybe you guys, what do you guys reckon what do you reckon the difference would be? And they say that the strength of the laser is the same, intensity is the same. So what might be different, do you guys reckon? Oh, so you're saying smaller peaks. The thing is, um, that might have been true if they didn't mention what happened to the intensity. But let's say that they're using the same intensity. So let's say that for this blue laser, it was I was about to write megawatts. Whoops. And then let's say for the red one, yeah, more spread out, yeah, larger width, yeah. So then whoops, milliwatts. So all we need to do is, so it's good. As you guys, some of you guys probably noticed that red spreads out more, so you're gonna have a greater width. So if we just do this again, what we'll basically get is it should be roughly in the mark scheme. They always mention that you have to have roughly the same peak. So I would suggest you guys measure this with a ruler, even though it seems like very long-winded, and make sure it's the same height. So if this was like 3 centimeters, we'll also do this three, but we'll make it a bit wider. So it might be something like this. Oops, it's meant to be a bit better, but oh well. Yeah, but anyway, so like it's gonna be the same height as that, but just what on earth am I doing? Just a bit more spread out. Yeah, so those are just questions they can always ask you. And that is pretty much the entire topic done. So yeah, that is the what's it called? The theory all done and mathematical questions to do with it. There is one last thing, and that's to do with what's it called? Path difference. So that's what we're using trig and stuff like that to do with this, which we can do on Tuesday. But that's pretty much all of it. So does anyone have any questions, or is it quite straightforward? I mean, the key thing is just understanding that like light can diffract through a space, and you guys basically get, you know, if you're using the same color light, you pretty much. Oh, the first practice question. Oh, this one, Raj. I know what we'll do. Rather than doing the same one, like let me give you a different one and we can end with this. So people understand they can do this and when they're done. And then at the same time I can explain this to you, Roger, as well. So let's just say I'll give you this. Okay, so I'll tell you guys that this is blue light is I'm not sure what the number is. Let's just say this. Let's say that this is, and they're saying what they're asking you for, what's the slit separation? So first thing is we write down the formula, which I already forgot, but I think it was something like W is equal to, probably have to check, wait one sec. I don't memorize these to be fair, which is not good. Yeah, it is that, yeah. All right, so we got this. So the formula is there first. And then what we need to do, Roger, just write down all the info that we have. So very basically, like we know what wavelength is. We know what capital D is, so it's distance between the slits and the screen, just the horizontal distance. The thing that's always a bit tricky is finding what this is. So W, if you remember, is basically the space in between dots or between fringes on the screen. Yeah, so this gap, that gap there or there or there, they're all the same. So we need to find out what W is. So if you look here, Raj, we basically have, how many gaps do we have? We got one gap there, two gaps there, and then three gaps there as well. Oh yeah, Alex, yeah, thanks for reminding me. I was about to ask you guys about that, yeah. I think we probably should, yeah, on Hangouts, then you guys don't have to type things out. So we'll do that for next lesson, yeah. So, well, that was quick, Leighton. So we got three gaps there. As long as Attila doesn't do his clapping voiceovers. All right, so we got three there. So basically, we got three gaps is 0.008 meters. So we just need one gap. So all you guys do is this divided by 3, and you'll find out what one gap size is, which is what W is. Are you okay with that bit? I think it's just like once you get how to find W, then that's probably the best. Yeah, so we get that, and then now it's just very simple. So we just need to find what S is. Now there is some sorcery you can do here. You see it with these kind of formulae in physics. If you want to find what S is, just replace these two. You can swap them around. So you get S is equal to this, and then you just put everything in the formula. And you get your answer. Yeah, so the key thing is it's not about the number of dots, it's about how many gaps there are. And then you divide it by the total length given to you. All right, so yeah, for next lesson, what we'll do is we'll use Google Hangouts. I think all you need is a microphone anyway. You don't even need webcam, so it's fine. You just need a microphone and I'm not a technical guru though. I'm not sure how. Wait, Alex, would I be able to use my camera to show what I'm doing there while doing Google Hangouts? Or would it have to? The thing is, Killing, you would get some light on the screen, but it'll be all in random places and it will not give you like a neat profile because the phase difference is not constant. So you might get some light there, then you might get like at random intervals. Actually, what we'll do is we'll actually do this in class. So we'll do it the incorrect way using just a normal lamp, and you'll see that you'll still get light, but it's just random. There's no like neat profiles, if that makes sense. Ah, I see. Okay. Yeah, I think what I'll do, we can just maybe use PowerPoints or something. The only reason why I prefer writing sometimes is because you can at least see like the thought process behind stuff. But I mean, there's benefits to both anyway. All right, so now that's done. The last thing you guys have to do is, what are those questions? Very simple questions. I think like if you understood this, you'll be able to like easily get 100% in these questions. There's only a very few questions. Shouldn't take you more than 20 minutes at most. Then he has the answers there anyway. So just spend like 20 minutes doing the questions and just email me if you need any help with it. Yeah, and if that's we said next Tuesday 2 p.m. So I'll catch you guys then. Oh yeah, killing. That's pretty smart. I will do that. All right, take care. Bye.